Good day, I am Shara's Ordejan, currently taking up Bachelor of Science in Ceramic Engineering at Mindanao State University Iligan Institute of Technology.
And I am Mitchevelle Jimenez, a ceramic engineering student at Mindanao State University Iligan Institute of Technology. Today we are going to present a review on the effect of magnesium fluoride addition on mechanical properties and thermal conductivity of silicon nitride ceramics as a requirement in our class CER133 Thermal and Mechanical Properties of Ceramics under Professor Raymond Virtudazo and Engineer Ordejan Arcasa. The contents of this presentation are as follows. Presentation outline. Introduction, objectives, problem of the study, methodology, materials, equipment, process flowchart, results and discussion, conclusion, and recommendations. The systems and machines of our world depend on power electronics for the ability to run efficiently and sustainably. Power electric devices have been widely used for a variety of applications, such as industrial robots, hybrid motor vehicles, and advanced electric trains. Due to the demand for more efficient control and conversion of electric power, power device technology is advancing toward high voltage, larger current, and greater power density. Since power electronics are advancing, it requires the use of substrates that has excellent thermal conductivity and mechanical properties to solve the dissipation of heat as the major obstacles in the progressing power electronics industry. Silicon nitride has emerged as one of the most promising substrate materials for the next generation power devices due to its combination of great mechanical properties and high thermal conductivity. To improve the thermal and mechanical properties of beta silicon nitride ceramics, the researchers put a lot of effort in using different raw powder, different sintering additives, and reasonable sintering process. Main objective: to know the effects of magnesium fluoride content on mechanical properties and thermal conductivity of dense beta silicon nitride ceramics fabricated by spark plasma sintering and post-sintering heat treatment. Magnesium fluoride is expected to decrease the amount of grain boundary phase and improve the thermal conductivity of beta silicon nitride ceramics because of high vapor pressures. Objectives: to obtain high thermal conductivity of silicon nitride materials, the following four objectives must be satisfied. 1. Full densification of silicon nitride ceramics must be obtained. 2. Phases in grain boundary should be reduced. 3. Eliminate grain defects and reduce the lattice oxygen content. 4. To know the best value of sintering additives concentrations for improving the mechanical and thermal properties. Problem of the study. There are still lack of research on the effect of magnesium fluoride contents on densification, microstructure, thermal conductivity, and mechanical properties of silicon nitride. Materials used. Number 1. Commercial alpha silicon nitride was used as the raw powder in this study. Number 2. Yttrium oxide and magnesium fluoride were used as the sintering additives for the silicon nitride. To investigate the effect of the sintering additives, yttrium oxide was set to 3 mol, while magnesium fluoride was varied from 0, 1, 2, 4, and 6 mol. Their corresponding samples were named as 3Y, 3Y1MF, 3Y2MF, 3Y4MF, and 3Y6MF respectively. To purify silicon nitride grains, isopropyl alcohol was used. The following equipment was used to conduct the study. Those are ball mill, rotary evaporator, vacuum oven, 60-mesh sieve, spark plasma sintering apparatus, X-ray diffraction, scanning electron microscope, universal testing machine, and laser flash apparatus. Process flowchart. Mixing. For 24 hours, sintering additives with their corresponding concentrations, silicon nitride balls and isopropyl alcohol were mixed in a ball milling process to obtain homogenized slurry. Drying and sieving. The Homogenized slurry was dried in a rotary evaporator at 65 degrees Celsius, then dried again in a vacuum oven at 110 degrees Celsius for 4 hours. Afterwards, the dried samples passed through a 60-mesh sieve. Sintering and post-sintering treatment. 5 grams of mixed powder mixture were placed in a graphite die, 20 millimeters in diameter. Then, sintered at 1650 degrees Celsius for 5 minutes under a uni-AC load of 40 megapascals in dinitrogen atmosphere in SPS apparatus. The sintered sample was annealed at 1900 degrees Celsius for 4 hours. Densities and phase identification. Using Archimedes method, the bulk densities of the sintered sample were measured. Phase identification of the ceramics was performed using XRD. Microstructure of the specimens was analyzed using SEM. Flexural strength and fracture toughness. Sintered samples were cut into rectangular bars. Using universal testing machine, the samples were tested after grinding and polishing. Thermal conductivity. Samples were cut into a disc with 12.6 mm in diameter and 2.5 mm in thickness and polished with 1.5 micrometer diamond slurry. Then, the thermal conductivity is measured using laser flash apparatus at room temperature. The equation K, or the thermal conductivity, is equal to density times specific heat times thermal diffusivity, were used to obtain numerical data. All samples 3Y, 3Y1MF, 3Y2MF, 3Y4MF, and 3Y6MF were subjected into this flowchart.
Figure 1 illustrates the displacement and displacement rates of samples with different magnesium fluoride contents during the SPS process. The displacements of all the samples reached the maximum value at about 1600 to 1650 degrees Celsius. It also shows that as the content of magnesium fluoride increases, the temperature of shrinkage decreases, which means that the initial liquid phase temperature decreased with the amount of magnesium fluoride to promote the densification of silicon nitride ceramic. Curves of displacement rates show a bimodal trend for all samples except for 3Y. Then the peaks of low temperature, lesser than 1500 degrees Celsius, and high temperature greater than 1500 degrees Celsius correspond to particle rearrangement stage and solution precipitation stage, respectively, as shown in Figure 1b. The formation of fluoride-doped liquid phase took place at a lower temperature as the temperature for the particle rearrangement stage decreased with the amount of magnesium fluoride. The densification and phase transformation from alpha to beta silicon nitride occurs as the peaks of shrinkage for all samples are about 1450 to 1520 degrees Celsius during the solution precipitation stage. Due to the reason that yttrium oxide is the only sintering additive used in 3Y sample, its curve of displacement rate contained only one peak at about 1450 degrees Celsius. Table 1 shows the densities of the centered samples 3Y, 3Y1MF, and 3Y2MF, which were centered using SPS at 1650 degrees Celsius for 5 minutes, which achieved a value of 99.6%. On the other hand, 3Y4MF and 3Y6MF were slightly lower compared to other samples due to an excessive magnesium fluoride content that causes the formation of silicon tetrafluoride to volatilize and thus lowering the density. All the samples' densities decreased slightly after annealing at 1900 degrees Celsius for 4 hours under 1 megapascals with nitrogen pressure. A decrease of the densities was accounted for the decomposition of silicon nitride in the sample surfaces. In this study, a pressure of 1 megapascals with nitrogen pressure was applied, which might have been enough to avoid further decomposition. The XRD patterns of the samples with different magnesium fluoride content before and after heat treatment were shown in Figure 2. Figure 2a, the encircled portion, shows the strongest peaks of alpha and beta silicon nitride. As the magnesium fluoride content increased, the ratio of beta over alpha also increased, due to the reason that the initial temperature of liquid phase decreases with the censoring additives, and the fluoride tube liquid phase has high solubility of nitrogen, which accelerates the phase transformation. As shown in Figure 2b, there was a complete phase transformation since there were no peaks of alpha silicon nitride detected by XRD in all samples after annealing at 1900 degrees Celsius for 4 hours. Y2SI3, 3, and 4 phase is observed in all centered samples, and it shows that no magnesium-containing secondary phase can be detected by XRD. Figure 3 shows the 10 micrographs of sodium hydroxide etched specimens before and after heat treatment. From Figure 3a, C, 3c, 3g, and 3i, the quantity of rod-like beta silicon nitride grains in the centered samples increased with the magnesium fluoride content due to the increased ratio of beta over alpha phase transformation. With the content of fluorine additive, the initial temperature and viscosity of liquid phase decreased, that leads to alpha to beta silicon nitride phase transformation and the growth of rod-like beta silicon nitride grains. Table 2 presents the mechanical properties of the samples with different magnesium fluoride contents before and after annealing process. It shows that as the magnesium fluoride content increased, the flexural strength of the samples decreased, while the 3Y sample reached the maximum value of about 1542 megapascals, whereas the fracture toughness of the samples increased with the magnesium fluoride content, and the 3Y6MF sample reached the maximum value of about 7.5 megapascals m to the power of 1/2. However, the flexural strength of the samples decreased, while the fracture toughness of the samples increased after annealing process at 1900 degrees Celsius for 4 hours. An elongated rod-like beta silicon nitride grain grew farther, and both the phase transformation and Oswald ripening occurred during heat treatment process. Due to the extraction and bridging toughening mechanism, the fracture toughness of the samples had improved, as shown in Figure 4. However, after annealing, the fracture toughness of 3Y6MF sample decreased because of the generation of excessive amount of volatile silicon tetrafluoride during the heat treatment that formed pores, as shown in Figure 4F. In Figure 5, the thermal diffusivity and thermal conductivity of specimens with different magnesium fluoride contents, which were centered using SPS at 1650 degrees Celsius for 5 minutes and then heat treated at 1900 degrees Celsius for 4 hours, were illustrated. After annealing and undergoing heat treatment, the thermal diffusivity and thermal conductivity of 3Y2MF were 35 mm² per second and 76 watts per meter Kelvin, respectively, which were 80% higher compared to the value before the heat treatment. At the end of the study, the effect of magnesium fluoride as centering additive on silicon nitride ceramic microstructure, mechanical properties, and thermal conductivity was investigated using SPS at 1650 degrees Celsius for 5 minutes and heat treatment at 1900 degrees Celsius for 4 hours. And it turns out that magnesium fluoride was an effective centering additive for densification, phase transformation, and grain growth of silicon nitride ceramic. The result also stated that it is possible to create a fluoride tube liquid process at low temperatures to make the ceramic dense and increase the phase transition ratio. Furthermore, the amount of centering additive, magnesium fluoride, required to achieve a high thermal conductivity value was 2 mol% with 3 mol% yttrium oxide. The thermal conductivity, flexural strength, and fracture toughness of silicon nitride were 76 watts per meter Kelvin, 857 megapascals, and 7.4 megapascals m to the power of 1/2 respectively for the optimum amount of additives that were mentioned. The accumulation of excessive volatiles was responsible for decreasing density and deterioration of output caused by the excessive addition of magnesium fluoride. For the review section, first, support of the theoretical background to the methodology. 3 conditions to achieve a high thermal conductive silicon nitride ceramic in the theoretical background were fulfilled. The silicon nitride grains were purified using isopropyl alcohol. Post-sintering heat treatment has been shown to be effective in reducing the oxygen content of the silicon nitride ceramic. Combining the post-sintering treatment and spark plasma sintering can be used to prepare high thermal conductive silicon nitride ceramic in a relatively short sintering time. Second, support of the theoretical background to the results and discussion. Our first condition to achieve high thermal conductive silicon nitride ceramic was satisfied since all samples centered by SPS reached full density. However, the phase transformation of alpha to beta silicon nitride could not be completed, and effects such as dislocations were left in the beta silicon nitride grains because of the rapid sintering. With the help of magnesium fluoride, high thermal conductivity value of silicon nitride was achieved, and phases in grain boundary were also reduced, which is the second condition to achieve high thermal conductive silicon nitride ceramic. However, there were some assumptions that were made by researchers in the study. For example, the decomposition of porous silicon nitride samples and formation of volatile phases were the possible reasons for the decreasing densities of fluorine-duped silicon nitride after heat treatment. Next, 3Y6MF has smaller grain size compared to other samples because there is a large quantity of small beta silicon nitride grains in 3Y6MF sample before heat treatment, while during the heat treatment, the growth rate of beta silicon nitride grain through oswald ripening is lower than through the phase transformation of alpha to beta silicon nitride because of the solubility and dissolution rate of beta silicon nitride grains were much lower compared to alpha silicon nitride grains with the same size. For the next review, there was no ludicrousness found since all data from the methodology, results, and discussion serves their purpose well in the journal paper. However, for the sintering additive, there were no explanations to why yttrium oxide content were fixed at 3%, so the researchers must have explained this and how the yttrium oxide content can affect the thermal and mechanical properties of silicon nitride ceramic. Our data was mainly focused on obtaining the data of the thermal conductivity, flexural strength, and fracture toughness as the mechanical properties of silicon nitride. So for the future researchers, they may have included all the mechanical properties of silicon nitride. For the results and the discussion of results in the study, they were organized and data obtained were properly explained. The researchers had successfully met the objectives and provided the answers to the problem statement. In general, the study was successful. And for the question, is citation properly observed? Yes, in the study, the citations and references were properly observed.
The study was mainly focused on obtaining the data on flexural strength and fracture toughness as the mechanical properties of silicon nitride. So for the future researchers, they may include all other mechanical properties of silicon nitride with the use of the same sintering additives and the same sintering processes for their future studies. Thank you.
And these are the references used in the study. And this brings us to the end of the presentation. Thank you for listening and thank you for your attention.